Hello, everyone. Thank you, Peter, for the introduction. Today we'll be discussing the work that I developed over the summer with Grigory Malinowski and Peter Richtarik over the VSRP as a part of a VSRP project. The title of the work is kind of self-explanatory, but I'll discuss what specific things in the title mean. So the question we are trying to answer in our work is, can the 5th generation local training methods support client sampling? And our funding is that yes, they can. And we present a method that actually proves that it's possible. And we present some variants of the methods just to complement the result. And also to show like specific cases of the method. Okay, so let's begin. So the problem we want to solve is of this form, which is an average of M functions. M is the number of clients. Each client is isolated. And whenever we do a communication round, then we need to communicate. We are communicating with one server, so this is more or less how it looks like. Each client has access only to its own function, and the gradient of the function. In our setting, we are assuming that communication is costly, and we would like to avoid it. And each computation that we do locally, like computing gradient, is actually cheap. And well, yeah, it's cheap, not free like zero, but it's cheap enough so that we can neglect it and just focus on the major problem, which is a communication. Okay, so we also assume that each of the local functions are L-smooth and mu-strongly convex. This is a standard assumption for local training methods. Yes. But what is a local training? Local training is the practice of like requiring each participant to do some additional computing before communication. I think there is an example of distributed local gradient descent. So instead of just calculating the gradient and then communicating the gradient and taking an average of the gradient to do one step on a server, we could instead do multiple local gradient descent steps and then communicate the resulting models and then average them and then broadcast the model to each workers and repeat the process. So that's like a simple example of what is meant by local training. Obviously, there is some merit to do that. If each functions were the same, we could actually skip the communication process and just do local training on each machine, then communicate once and have the answer, right? Because each worker would find the same answer for the same problem. So it would definitely work. We would skip a lot of communication and we would find the solution. So it makes some sense. It's not bulletproof though, right? So I'll briefly touch like the generations of local training methods, right? So the first generation, I believe like 2015, 2016 are heuristics, which have no theoretical guarantees. However, they are proving empirically that it makes sense to do some local training before communication. That's nice. The second generation assumes some similarity of local functions. I believe like bounded gradients or something like that. And they provide some guarantees, right? But the similarity assumption is something we wouldn't like to have, right? The third generation predicts sublinear rate, which means that it predicts that it's better to avoid doing local training instead of just doing like normal one calculating of gradient and then communication, which is bad. Well, it's not bad, it gives some guarantees, but it predicts that it's actually worse than just doing what we were used to do. Then we have the fourth generation, which predicts that local training is more or less the same as not doing local training. And the fifth generation is the accelerated age of local training methods. And the first instance of the accelerated methods is ProxKeep, which predicts the same number of iterations of the algorithm. However, only the square root of those iterations has to be our communications, right? It's more complicated than that, but it's amazing, right? So, and I believe ProxKeep was developed in this year, 2022. So it's relatively new idea to have the fifth generation's local training methods. And in this talk, we will be talking about another instance of the method. However, an instance that supports client sampling, which is the practice of using just a subset or like a cohort of clients at each iteration to each communication iteration to do the training, right? So
Michał, I have a very quick comment. So I just noticed that all the authors of ProxKeep are here in this talk right now.
Oh, hello everyone. I really like your work. I'm a big fan. Okay, it's an honor. Okay, so this is a brief overview of the fifth generation local training methods. Well, as you can see, all developed in 2022, so relatively new idea. We are also discussing the local training solver because it will prove to be an interesting question that we also briefly answer in our work. But as you can see, neither of the methods support client sampling, and only our work does. So this is more or less the starting point of our work. We see that, we already have few methods that fall into the category of fifth generation local training methods. However, neither of them support client sampling, and it is not even known whether it's possible to design a method that would enjoy communication acceleration via local training and at the same time support client sampling. And we wanted to solve that question. To do so, we need to reformulate a little bit our problem. More or less, that's it. We'll just introduce some naming so that it's easier to talk about the functions. But the basic idea is that since our functions are strongly convex, we might use this strong convexity a little bit differently, and this other convex function, which is also smooth, we could use it differently. So we can kind of have like this like a proximal update for each of those components. And what we want to avoid is obviously calculating a proximal operator of this part. However, we don't worry about calculating the proximity operator of this part. So what we did was taking a method that have client sampling, however, requires us to calculate the proximity operator of this part, And we just solved this problem inexactly, and we proved to what approximation we need to solve this problem, with problem of calculating the proximal operator of this problem, to enjoy the acceleration and provable convergence. So that's more or less what happens in our work. Yes, okay. So the naming we introduced is of capital F. The capital F is just so that we don't have to, whenever we refer to this object, we don't have to actually spell it out. We just say FM, capital FM is, this, right? This object is convex and LF smooth. Whenever I will discuss the convergence result, I will be, talking about the original L and mu, so that we don't have any, confusion here and there. However, it was just a simplification for the proofs, I believe. So, nothing to worry about here. Okay. Now we do the standard trick, which gives a freedom of each x at each local x to be different, and since each FM is stored, capital FM is stored in a different client, we allow it to have a different model, right? And then we introduce a linear operator that basically takes this freedom away. So it takes one x and spills out m individual copies of x, so that there is actually no freedom, right? However, it simplifies a little bit, because now we end up with a structure when the original problem is written in a way where we have a smooth and convex function, which is a concatenation of a function and a linear operator, and a strongly convex regularizer. And our method is developed for this type of object. However, as you can see, it's very similar. It's very simple to change the original average of the functions to this type of problem, and then apply our method to solve it. So that's the reformulation. Is it clear to anyone? Are there any questions to what was going on? What's H, or what's what? So that I can go further. Okay, if you have any questions, then just ask them. It was very brief. I don't want to spend too much time on just the reformulation, because it's not very important. But well, it is important to understand the method, but it's not a crucial founding of the work. This is the algorithm. It might look sus, however, it's actually not very complicated. So there are some dual iterates. We don't have to worry about them too much at the moment. Just think about X is the model, and we want it to converge to X star, which is defined to be a solution to our original problem. This solution is obviously unique because this F is strongly convex. So there is no ambiguity here, right? And we want it to converge to, we want X iterate to converge to X hat. To give you a brief intuition on what the algorithm does, it predicts an update. In the fifth line, you can see we compute X hat, so that this is our prediction to what an X iterate could be. Sometimes it's called X t plus half. That's something you might stumble upon. People sometimes use that naming, but we prefer X hat. It looks a little bit cleaner. That's our initial guess. And this is actually what I meant by saying that we use a proximal operator, because this X hat t equal to something, this is actually a proximal operator of the regularizer. right? We don't care about calculating that because it's actually simple to solve this problem, right? So that's instant, right? Because we can just write it out. It's fairly simple, and we choose a cohort of cardinality C. So only C clients out of M will participate in training. Then we broadcast the X hat to those clients, and then each of them locally finds an approximation to this type of problem. You can see it starts in line 7, and this is the problem. Let's refer to it. It's phi mt, right? So each client has like a phi function. It evolves over the training, right? Because x hat t and umt evolves over the training, so the local problem actually changes over the span of training. It evolves so that at the end of training, each local function has actually the same solution, which is a solution to the original problem. That's why we can actually manage to solve the problem via using the local training, right? Because the local problem evolves to have the same solution as the original reformulation. Okay, and this line, so the 7th onwards, is an interesting thing that we'll focus on a little bit later. But for now, you see that only C of them participate, only C of clients participate in training, and the rest does nothing. You can see it in the line 11. The rest of the clients do nothing. And then in the line 14, we see that we kind of do a correction for our initial prediction. So we have x hat t, and we do some something funny to it so that it actually does converge. So it's like a correction. You can think about it this way. I like to think about it that since we are doing a local training, we can kind of expect our method to locally find something stronger than just a gradient, because the gradient information tells you exactly where you need to go in this moment. However, because you're training and you're gathering more information over the span of training, potentially there is a way to modify your local problem so that the information you can gather is stronger, and this is more or less what we are doing. For people that are familiar with proximal operators, you can see that this phi is actually argmin of psi is actually a proximal operator of capital F M, right? So we don't need to calculate it exactly. We just needed to approximate it well enough. And how exactly I'll discuss this later. Firstly, I'll show a few simple examples, 2 simple examples of this method. One which is called mini batch point saga. Sometimes we refer to it in our paper as 5G CS infinity, which solves this local problem. So the problem 5 exactly. And you can see it's written in line 8. This is just well, it might not look identical, but it's just a Moreau identity applied to the proximal operator here, I believe. So this is just written differently, but this is like a closed form solution to the problem in the line 5. So we have this method, and it's and the only difference between this method and the previous one is that it finds the solutions exactly, and the communication. That's kind of important. We will be talking about only communication rate. I will touch on the the local rate, how fast we can solve the local problem later, but this is something we wanted to have. We wanted to have client sampling and also the communication acceleration. So the communication, the number of communication iterations will call T, and we'll compare the methods using this T value. And the number of communications needed to solve the problem is actually optimal for the setting, which is a square root of kappa multiplied by the square root of like the reverse of the participation, so m over c, square root of it, plus m over c. So yeah, we'll come back to that later. And the other instance of the method, which is kind of like a toy example, is the original method 5GCS, however, with no local training. So we just take the first iterate, and instead of doing iterations and like finding the approximation, we just take it and do the update. But like we just calculate the gradient once. We're doing no updates, and we are arriving at this method. I think we refer to it 5GCS0, reasonable, I believe. And you can see the dual update just becomes the gradient of the capital FM at x hat. So that's interesting, and we prove in the paper that this method also converges, and it has communication rate of m over c times kappa, which is reasonable. It's to be expected. I think it's standard for methods that doesn't have any accelerations. So this is just a non-accelerated method. However, it doesn't do any local training, so that's to be expected. I think I touched on this problem a little bit, so I might skip it actually, or maybe some of you have questions. Okay, maybe we can talk a little bit briefly on what we say here. So we say that we want, this is line 7 out of this algorithm 1, 5GCS. We want locally to use some local optimization algorithm, AM, to do k iterations and find ymkt, let's say just final point of the k iterations of some method, which has to be approximating the solution. So you can imagine just taking this problem in line 5 and applying gradient descent to it, running it for k iterations, calculating the gradients once more, computing umt+1, and then broadcasting it, sending it to communicating it to the server. And this is done only on the clients that participate in the training. The other clients just update umt+1 to be umt, and they do nothing else. So for this method to converge, we need some assumption on how exactly the local problem has to be solved. And this is the exact kind of thing that pops up in the proof that we need to satisfy. However, it's very reasonable, and it's actually way simpler to satisfy this than one might expect. So the AMs can be any subroutine that minimizes the functions, right? And the final iterate has to satisfy this inequality. It's important to know that what's on the right-hand side, this is the solution to the original, not to the original, to the local problem, so to the psi m t. And this is the starting iterate. We are starting iterating at this point. And this is just a gradient of psi. Gradient descent can, for strongly convex functions, which the local problem is a strongly convex function, can predict how the the norm, the square norm of the gradient of our iterate shrinks compared to this value, and same goes for this object. So the last iterate and the solution, this also shrinks relatively to this value. So it's actually very easy to calculate what we need given the subroutine that we want to use, if it's one of those standard ones that actually do converge, because we could just guess any point and this would have no guarantees, right? It's nice to note that if we just satisfy this inequality for some epsilon tau, it's just some combinations of those objects. I didn't want to write it all down, but if we satisfy this type of inequality with an appropriate epsilon, then the assumption 2 would be satisfied. So this might be more familiar to most people, right? So this is just a square norm of the current iterate, and this is the relative value to which we want it to be smaller to, right? So for example, gradient descent has a convergence rate of L over mu times log 1 over epsilon tau, right? So that's, yeah, I hope it looks less scary than this. Okay. So now we can talk a little bit about the main theorem and the main corollaries and main results, and basically the main algorithm of the paper. So the 5GCS with a local solver being gradient descent do converge, because gradient descent converges and can satisfy this inequality. Will converge with optimal communication rate, given that k is bigger than k is the number of local iterations, given that k is bigger than this object. It's fine. We have some log term here that it's not ideal. Maybe we would like to get rid of it, but this is not something that we're focusing too much while developing this theory, because we wanted to have a method that is an instance of fifth generation method and also enjoys the client's sampling, supports client sampling. So maybe it's something that for the future analysis. So the convergence rate that we are obtaining is actually the same as if we were solving the problem exactly, which is very interesting. It's actually, we find out that we don't need to find the solution exactly. We just need relatively good approximations to obtain the same communication rate. We'll show some plots on that later. So the experiment part is, it was actually way harder to design the experiments than we might have thought, because there's no other fifth generation method that supports client sampling. So there is very little method that we can compare our method to. So the function we are minimizing is the logistic regression, which is L2 regularized. This problem is L smooth and lambda strongly convex, because this object is just convex. And we do 2 experiments. We run our method relative to all other local training methods. with full participation first, because this is the setting that our method is still accelerated and still can be compared to other methods, right? However, it doesn't have this client sampling in it. And well, as we can see, our method is definitely in the accelerated regime, because it's actually like a square root faster than the other methods. Probably we didn't run the other functions long enough to see whether they actually converge, and also the plot would be very long. So yeah, as we can see, we're only losing to proc skip, which is fair. The proc skip is very tight in the analysis, so it's okay. But an interesting thing is that I think it's visible here that the number of communication rounds we need is 16/3 times this object, which in the partial participation regime is just a square root of elm omer mu. So it's approximately 5, and proc skip doesn't have this 5 here. So you can see that, if the proc skip analysis is tight and it's exact, then our is also exact, right? Because it's approximately 5 times worse. So given they're right, we are also right. But that's an empirical result. It's look nice. And the other experiment we ran was with the client sampling, and as you can see, only our method is accelerated in this client sampling regime. The other methods, some of them converge, some I think only to the neighborhood. Yeah, I'm not quite sure, but only our method is accelerated. And we also did a naive implementation of proc skip with client sampling, and as you can see, it diverges quite quickly. So if we want to see proc skip with client sampling, then we have to be a little bit smarter than we were during the development of the experiments, because it didn't work. It diverged. But there's no more experiment we could do. Maybe we could run some funny stuff, but there were no other methods we could compare our method to, because it's the first instance of this type of method. Again, we have the whole proof of the convergence of the method with client sampling in the original paper. I will not go through it because it's long and boring, but I recommend reading it because it's actually interesting. Okay, so now we'll touch on something very interesting. So dependence of capital T on capital K. The T is the number of communications and K is the number of local training iterations. So we wanted to see whether there is any dependence on how many local iterations we do and the speed of communications, whether we can actually do a little bit less local training and then have a little bit worse communication rate, and maybe we can do more of the local training and then have better communication rate, and whether we can actually predict it and theoretically prove that the method like that would converge. So yeah, this is kind of the idea behind it, and it is actually true. We have a theorem that we create like a dependence of K on the lambda object. It's alpha on the alpha object. As you can see, I'll go to the original theorem. Here we have a constant times log of kappa, 2 kappa to 4 kappa, something, log kappa more or less. And we have here, we just have a constant, and when we reach this threshold, there is actually no benefit on the speed of communications. However, we wanted to see whether this constant can be smaller and how would that affect the communication rate. So that's kind of the idea why we just put an alpha here and did the whole analysis not again, but did the whole analysis and see how it how the theory works in this setting. And we can see that the whole theorem is more or less the same. We just need to put if we have lambda between this, between this, how do you call it, like interval, then the whole theorem just follows, and we will get that the converges. I believe that the communication, I think that we have, we have the corollary written here. So if the lambda is the number of the local training iterations for gradient descent, because it's important, we are solving the problem using a gradient descent, it will be hard to do such analysis for an arbitrary method, because we'd have to add a lot of assumptions on the method probably. So T is predicted to be more or less 1 over the number of local training steps of gradient descent. It's obviously multiplied by a lot of constants and added something to it, but it's more or less, we can see this kind of trend, which we were nice enough to present in this nice graph, which is just a theoretical graph. It just plots this corollary. So it's just an example of how the dependence on of T on K would look like. So we can see that from the smallest number, so when alpha is close to 1, so this is the this is here at the beginning of the plot. I hope you see my mouse. If you don't, then well, sorry. We can actually see that the rate that the communication rate that we predict is not accelerated at this regime. It is a little bit faster, I believe, because instead of m over c multiplied with L over mu, we have the sum of it. So that's already accelerated, right? Because we are already doing some of the gradient steps. However, we see that the more local steps we do, the faster the method will converge. And finally, we reach this point where alpha is in this upper spectrum, where there is actually no improvement from that point onwards. We call it an optimal zone. There is no need to do more of the local steps of gradient descent. Where we are in improvement zone, and probably it's a good idea to do more local steps if we can actually allow for it. It depends on how much we value local calculation over the communication. And as you can see, there is some obscure zone here that it might be the problem with the analysis or with the method, that given a gradient descent, we don't actually know what happens in between 0 and here. Well, we know that for 0 the method converge, and we know the rate of it, and then we just have the analysis from this point onwards, right? So in this interval. And here we just have a plot when we were running this original function with a different number of local gradient descent steps, and we're looking at how fast the method achieved an epsilon solution. And we can see that the trend is relatively similar to the one that the theory predicts. So the more local steps we are doing, the faster the method converged in communication. And after some point, I believe here 135, So in this last dot, the improvement is not really there. Yeah, so that's more or less the dependence of the method. Are there any questions? Because I think I might step a little bit out of time.
Well, you're still within time. We have an hour for this, but of course, allowing for questions is a good idea. So please raise your hand or write a comment. I'll try to unmute you as usual if you want to ask something. I'd love to hear your voice rather than just read out your question aloud. So while people are thinking about questions, so you mentioned 135 as a special point on that plot. Can you say in what sense it is special?
Yes, it's special because this is exactly the point where we predict that from this point onwards there is no improvement. There's no benefit on doing more local steps. So it would be the point which is respective. It's it's like it's this point, but for some specific data. So I believe that we use the partial participation of 20%, and the L over mu was like 10 to 4. So math, and it was 135. So that's kind of why this point is special.
So in full participation regime, it'd be square root of condition number, right? But this is square root of condition number times square root of this partial participation condition number or something like that, right?
Yes, yes. That's also interesting that actually when we do the client sampling, we don't need to solve the local problems as accurately as we would have to solve them in the full participation regime, right? Because we have in the the assumption is not written in a very informative way, I believe.
So what do you say is not square root of m over c, but square root of c over m?
Yes, it is. Or maybe in the main theorem it should be visible. Yes, so for example here, right, for the gradient descent run, we have the square root of c over m, which is interesting, right? Because if c is very small, then the k doesn't have to be as large as it would be if c was equal to m, right? Because that would be 1. So that's an interesting thing. Maybe it happens because we don't want to bias our iteration too much for like one function. If we only have one function and we just do the whole update relative to one function, then it might not be so useful, right? So we don't have to be very accurate, something like that. But it's just interpretation.
Okay, so I clicked on everybody ask to unmute. So I believe you should be able to unmute yourself if you wish to ask something. If not, shout or wave your hand at me or something, and I'll unmute you. Any questions?
Okay, hello, I'm Sebastian. Okay, thanks for your work. Very interesting, many details. I'm a bit lost, but let's say when I read the title, I was expecting some version of ProcSkip with client sampling, but now we see a different algorithm with client sampling. Could you comment a bit on the differences to this ProcSkip version with client sampling? that you implemented, and what exactly is new in the scheme that you have now? I mean, I see that the prox is different and so on, but could
Okay,
you comment a
so
bit on that? Yeah.
I'm not an author of Proxkip. If we have more questions about Proxkip, we can maybe ask the authors because all of them are here. But one of the like nice improvement, not like difference that we have here is, for example, that the number of iterations that we do locally is actually discrete. You can calculate the number of iterations that you would have to do given a method, given an algorithm, local algorithm that you want to use, and then calculate the approximate number of iterations to guarantee convergence, and then you just need to run it for this number of local steps. In Proxkip, it's a little bit different, right? Because the number of iterations over one communication is actually distributed given like a geometric distribution. So it's a random variable. So that's, for example, one difference. The similarity, for example, is that we also have a like dual iterates that evolves our local problem to have the solution of the original problem eventually, right? So that's kind of a similarity that we have here and there.
Yeah, no, exactly. Okay, I see. No, I mean yeah, exactly. So in Proxkip, the number of local steps was sort of given, but you need a certain accuracy to hold. Yes, and basically you solve a proximal problem on every client to certain accuracy, and this was it's very different from what we tried with Proxkip or something.
Yes.
Okay, thanks for.
So there's one way to think of it, Sebastian, just to add to what Michał said. So one can think of both Proxkip and this as being somehow randomized version of primal dual Daviesian splitting, but different ones. So there's one way to think of it. So I mean, you've tried, right, and others tried, and Kostya tried, and Grisha tried, and so on. So many people tried to make Proxkip work with partial participation, so somehow it didn't work out, right? And so we're thinking maybe something else should be done. I mean, that doesn't mean that Proxkip cannot be made work. I mean, maybe it can. I mean, I'd be very surprised if it couldn't somehow. But this is just different approach. And one way to think of it really is that different randomized version of this PDDY, but another one would be to think of it this way, that everybody knows the point saga algorithm, and one can think of it as some kind of extreme version of partial participation, where only one single client participates, and that method has accelerated communication complexity. However, it essentially needs infinity of local training steps because it evaluates the prox exactly. So the question is, can you do that with finitely many and reasonably many local steps? And it turns out square root of condition number, roughly local steps is enough. And you can also parallelize, so you can make it mini batch, and then you really get partial participation version of some kind of an accelerated method, local method. So the different algorithm, but kind of very similar theory. Also square root of condition number local steps, also square root of condition number communication rounds, and so on. But this one allows partial participation.
Good. Okay. Thanks for the explanation. Yeah.
So anybody, I believe, can unmute themselves if you have any questions. Okay, so I have one question, a fake one, obviously, but I'm going to ask it anyway. So there's this assumption that you had there on sum of all over all the clients have to satisfy something, and this seems to have this interesting potential implication that some of these clients can do maybe less work and others can compensate for it. Can you maybe comment on this?
Yes, sure. So as you can see, this assumption requires the it's actually talking about the like a square norm of a large vector of YMs concatenate stacked on top of each other. So we are actually thinking about the solution to the this FH problem. So not exactly to the only the to the individual local ones. So the assumption that we need to satisfy is actually this, and as you can see, if we have this satisfied for an appropriate epsilon, then this would also be satisfied, just because this inequality can imply this inequality, right? However, if we leave it in this form, this gives us a little bit of space, right? So let's say some of those objects could be, let's say, bigger or smaller if some of the local functions, let's say we allow them to have different smoothnesses or different condition numbers, because our theory allows for that, then we might actually want to solve more difficult problem more exactly, let's say, so that a different problems doesn't have to do as much work. And this assumption can be satisfied if, let's say, some functions can be solved very to the very small accuracy, very accurately, and other problems are not solved as accurately, then this joint assumption can be still satisfied. So that gives us a little bit of space, right? So if some clients are, well, say the devices are stronger, for example, we can run more steps of gradient descent. And if others are a little bit weaker, then maybe we can compensate for that with stronger devices. So that's kind of the hope here. It's not formulated theoretically, right? It would be a little bit difficult to do. However, it kind of gives a potential way of improving this method to kind of take it into account, right? Yes.
Yeah, so just to summarize in a few sentences, this seems to be a new phenomenon in federated learning, or at least something that I haven't seen people talking about, which is that not only this local training helps to I mean, leads to communication acceleration, so it helps the training process, but there is some interaction between how much local training all clients do. These are not completely independent processes. So if somebody does not do enough, maybe others can compensate for it by doing more local work, because all that needs to happen is that some of these M numbers, capital M numbers, has to be smaller than the right-hand side. If some of them are large because those clients are lazy or busy or whatever, they don't do that much work, others can maybe decrease their own numbers so that the overall sum will satisfy this inequality. So there's some level of collaboration or cooperation or whatever you want to call it that is at play here. Okay, any other questions? After my fake planted question has been answered.
Very good question, and also a very good answer. Thank you.
Yeah, sorry for that. So maybe we can turn it around and ask, Kostya, Sebastian, Grisha, why does proskip not work with partial participation, or is there any hope, and so on and so forth?
I have a very short answer. You need a new version of proskip. You need proskip 2.
Proskip 2023. Okay.
Whatever. Yeah.
I'm happy to ask another fake question, but in case you have questions, go ahead. So another fake one would be this, but this is not completely fake. So what is not answered by all of this that you talk about? What is not understood? So what remains to be resolved?
What remains to be resolved by the theory of our method?
Yes. So what is the weakness of everything that you've talked about? How would you criticize your own work?
Okay, so for example, to find K, right? This is something we touched a little bit, right? We need to know what the condition number of a local problem is, right? We know tau, so that's nice. However, we might not know L exactly. So finding K might not be easy. So, and we need exactly K or more a number of iterations to guarantee convergence. Proskip doesn't have that, right? Because once we choose step sizes, we know the expected number of iterations that we need to do to guarantee convergence. So this problem of condition number happens only if we want to have the optimal number of communications. Here, this problem appears more often, even if we don't want to have optimal number of communication numbers. If we want this method to converge, then we need to know that. So that's that's problematic a little bit, but it's all right. Let's see. Well, also, one problem could be the existence of this log term here. Maybe it'd be nice to get rid of it, right? So that we don't have to suffer this this additional log term here. Maybe you can change it to something else, something smaller. Well, it's still pretty small, so it's all right, but that's kind of a like a drawback of the method, that we need to do a little bit more iterations than proskip say, right? Because proskip just in the full participation setting, does a square root of L over mu, and we need to multiply the square over mu by this log term. So that's something could potentially be resolved. Yeah, but on the other hand, the strength is that like if I go to this table, right, the LT solver can be anything that satisfies this this assumption, this joint assumption, and any optimization method. So it doesn't have to be gradient descent. This is just an example so that we can present a little bit more, show that it actually can be satisfied, right? So that's why we chose gradient descent, but it can be anything. It can be stochastic gradient descent. It can be Nesterov accelerated gradient descent on any variant of that. So that's kind of that's good. That's maybe a choice of solver can solve this log term potentially. Do you have any specific weakness in mind?
No, I didn't have anything in mind. So obviously every work has lots of weaknesses. Doesn't apply to convex setup or non-convex setup, for instance, right? And so
yeah, true.
And so true. Yeah. Do you think this factor 16/3 or whatever that was, roughly 5, it might be improvable so that this gap goes down?
Yes, it can be improved. This is what you're talking about, right? So it can. I believe that we made that choice so that it's true for every for every problem which is smooth and strongly convex. However, if we actually have this kappa being bigger than 5, say, then I believe we can make this this constant way closer to 1, like almost 1. It can't. I think it might never be actually 1, but it can be very close to 1, given the completion number being, large enough, and this large enough is like 5, maybe 10. It's a relatively small number, but we didn't want to introduce more ambiguity or like to confuse anyone with an additional way to choose gamma and tau. So that's kind of the reason we just settled for this for 16/3. That's kind of why it's here.
Okay, thank you.